Okay, the pH scale is a logarithmic scale, base 10, that measures the amount or is an indication of the amount of H plus in solution. So mathematically, pH is defined as the negative log of the molar concentration of H plus in solution. And in fact, what you'll note over time, we're going to use a lot of things with a little p out front, like for example, POH, eventually pKa, etc. And in all of those cases, all that means is that little p indicates a negative log and a log scale kind of thing. Right. The reason that pH, because it's based on the amount of H plus in solution, and the amount of H plus in solution is often very small, that's why this whole thing is a log scale. So just to give you a sense of how small these amounts are, remember that neutral solutions have an equal amount of hydroxide, and when I say amount, I mean concentration, molar concentration of hydroxide and of H plus. And if we are at 25 degrees Celsius, where the Kw, so the auto dissociation constant of water, is 1.00 or something like that times 10 to the negative 14th. In those situations, right, that neutral solution, it means that we have 1 times 10 to the negative 7th molar, that should be a 7, not a 3, 1 times 10 to the negative 7th molar hydroxide and 1 times 10 to the negative 7th molar H+. So that's not even looking at basic solutions. We're already looking at very small concentrations of H+. Again, why we decided to make this, we as chemists decided to make this pH scale logarithmic. More ramifications of this, a change on the pH scale of 1 is equivalent to a change by a power of 10. Change to the H plus concentration. So small changes in pH mean large changes in amount of hydrogen or ions in solution, the number of protons in solution. Just a brief kind of orientation. A pH scale, we're going from 0 to 14 at 25 degrees Celsius. This is based on Kw, which is where we get the number 14 from, the negative log of 1 times 10 to the negative 14 is 14. So on that 0 to 14 scale, we've got a couple landmarks, right? 14 is very basic. 7 is neutral. 0, and actually they're even negative values, are very acidic. And all of the ranges in between. The POH scale, which is a measure of the concentration of hydroxide ions in solution, is just the negative log of hydroxide ions. It just goes the other way around. So if this is the pH scale here, the POH scale, 14 means, actually I should do it this way, 0 means very basic, 7 is still neutral, and 14 means very acidic. Okay, so POH and pH are you can use them in the same way. They're just measuring the concentration of a different ion in solution. All right, so anytime I know one of these quantities, pH, POH, the concentration of H plus ions or the concentration of hydroxide ions, I can actually already have all the information I need to figure out all of the other ones. So if I know one of these, I can calculate them all. All right, and using this kind of box of calculations is how I've taught this for a while, so I'm just going to go for it. All right, When you're going between POH and pH, you're going to use the relationship that you can kind of already intuit from up here, right? 0 plus 14 is 14, 7 plus 7 is 14, this plus this, 0 plus 14 again is 14. All the numbers in between kind of align up in the same way. Essentially, 14 is equal to the pH plus the POH. So if you have the pH and it's 8, then you know the POH is 6. All right. We already talked about how do we, if we have H plus concentration, how do we go to pH? Well, we take the negative log of the H plus concentration. Okay, the negative log of H plus concentration. If I'm going from the pH to the H plus, those of you who remember your log rules really well know how to do this already, but that's going to be 10 to the negative pH, because to get rid of a log, you're always going to raise the whole quantity well, you're going to raise 10, the base of that log, to the logged value. Okay. If you do not remember your log rules, you can either memorize this or you and I can talk about it a little bit more in depth at some other point. Right, H plus and hydroxide, these two things are related by Kw. All right, so Kw, whatever it is at whatever temperature you're looking at, is going to equal the concentration of H plus times the concentration of hydroxide. Okay, and then POH and OH minus are very similar to the pH H plus. If I want to go from hydroxide to OH to POH, I'm just going to take the negative log of hydroxide ions in solution. If I want to go back the other way, I'm going to take the raise this 10 to the negative POH. All right, let's do one because there's also a kind of funky, weird sig fig rule. Okay, and that funky, weird sig fig rule is that the number of sig figs in the concentration, so like in the normal unlogged values, is the number of decimal places, so places after the decimal point, in the pH value. All right, so to do a quick sample calculation here, let's say we have a pH of 3.22, and we're being asked to find the H plus, the hydroxide, and the POH for that. All right. You can go any way around that you want. You can go from pH to POH to OH to H plus, or you can go from pH to H plus to OH to POH. No one cares. I'm going to go from pH to H plus, so I know that 10 to the negative pH is equal to the H plus concentration, which in this case is 6. And now looking at my sig figs, right, I'm looking for a concentration. I know that the number of sig figs in my concentration has to be the number of decimal places in the pH. So I just want 2 sig figs, so 6.0 times 10 to the negative 4th is my concentration of H plus. Right, I know that Kw, 1 times 10 to the negative 14th, divided by the value of the concentration of H plus is going to be equal to the concentration of hydroxide. So I'm going to get 1.7 times 10 to the negative 11th molar hydroxide. And last but not least, I'm going to take the negative log of that, 1.7 times 10 to the negative 11th, to find the POH, which is going to be 10.78. And now again, the number of decimal places is the number of sig figs in my concentration value up here. And that is how you do all those calculations and apply the sig fig rule. All right, last but not least, when does this really come in handy? Sometimes we're going to be asked to calculate the pH of various acid or even base solutions. We're going to stick to acids right now. Anytime you're being asked to figure out this, really the first thing you're going to be looking for are, is this a strong or is this a weak acid? So I've got two different problems up here, one with 0.645 molar HNO3, one with 0.645 molar HCN. First off, you will have to memorize what the strong acids are. The strong acids are HNO3. Can I do this from memory? We'll find out. HCl, HBr, HI, HClO4. We got HNO3 already. H2SO4. 1, 2, 3, 4, 5, 6. I feel like there might be one more. I did not actually write all these down prior to starting this pencast, but that's okay. All right, anyway, HNO3 is definitely on that list. This is a strong acid. So what are the major species in solution? Well, they are H3O+, which is what we are commonly referring to as H+. It's just what H+ does in water is it will join up with a water molecule. We've got NO3-, and we have got H2O. That's pretty much it for the major species, but if we wanted to do minor species, we would have to remember that there's also hydroxide in solution. Those hydroxide ions don't go away even if you add a lot of acid. Because this is a strong acid, what that means is that in this case, the number of H+ ions is equal to the concentration of HNO3 ion, or HNO3 molecules, right? Because it's going to dissociate completely. So those two things are equivalent. What that means is that pH is just going to be equal to the negative log of the concentration of HNO3 that's given, because that is the same as the concentration of the H+ ions, and thus the pH we can calculate as 0.190. Now with my HCN, it becomes a little bit more complicated because I look at this list, I say HCN is not on there. My other clue here is that I have a Ka, and it is not a big Ka. That's 6.2 times 10 to the negative 10th. That means that at equilibrium, there's many more reactants than products. What equilibrium reaction are we talking about? Well, for Ka, remember we're talking about the equilibrium equation where HCN is going to dissociate in water into H+ and Cn-, or we could say that HCN plus H2O goes to H3O+ plus Cn-. Both are equally valid. Okay, so in this case, what are the major species in solution? Major species in solution are going to be HCN and H2O. The minor species in solution, they're still important, but they're minor, are going to be H+, Cn-, and also, again, a little bit of hydroxide floating around. Okay, so how do we figure out, and again, what this means as well is that the concentration of HCN is not equal to the concentration of H+, and that's going to be true for any weak acid. All right. Essentially what this question is asking, or rather what the pH is going to be dependent on in this case, it's going to be dependent on the equilibrium concentration of H+. So what we're going to need to do in this situation is do an ice problem, okay, because we need to figure out what the concentration of H+ at equilibrium is going to be. We know we're starting with 0.645 molar HCN, 0 H+, 0 Cn-. This is a pretty easy one in terms of minus X plus X plus X. All right. We have a very small Ka, and we're starting with only reactants. Thus, we know that X is small, and we can omit it in the denominator. Oops. X squared equals 0.645. Okay, that's our Ka. That's our setup here. We solve for X, and we obtain lots of 9s. Here, I'm just going to carry it out so I don't have to try and round that all to 2 times 10 to the negative 5th molar. Right, we're not at the end yet, so I don't have to worry about rounds. Sig fig rules. Remember, the concentration of X at this point is the concentration, the equilibrium concentration of H+. So now I just have to take the negative log of that value, which in this case gives me, now I do have to pay attention to significant figures. I started with 6.2, so I would say I have 2 sig figs. And in terms of pHs, that means that I have 2 places after the decimal point. So I'm going to round my value 4.70. That's going to be the pH of this solution. You can see the same concentration of HCN has a much, much less acidic pH than that same concentration of HNO3 in solution.